Yeah, good morning, everybody. So, welcome to the first session today. And today we have the first speaker, Professor Parthasarathi Mukhopadhyay. I will give little introduction about him. Dr. Mukhopadhyay has done MSc in Physics and MTech in Atmospheric Science from Kolkata University. He did PhD from the Pune University in 2005. He has 30 plus years experience in the numerical weather prediction, development of the dynamical core, and the physical parameterization. The India's first kilometer scale model, the Bharat forecasting system, was developed indigenously under the leadership of the Dr. Mukhopadhyay. He has published 100 plus peer-reviewed papers and guided 14 PhD students. He has obtained the Fellow of Indian Academy of Science in 2023 and received the award of certificates of merit from the Ministry of Earth Science Government of India. He just retired last year from the IITM Pune, where he has worked more than 30 years. And sir, now the floor is to yours, and you may take 45 minutes so that audience will get a lot of time to discuss the questions and answers.
Yeah, thank you. I put my stop. Okay, thank you. Thank you, Bipin, for so long and kind introduction. And thanks to all organizer and Dr. Adway and Vishal and everyone for organizing such an excellent, summer school or something, whatever, training. So, okay, I was told to talk on this recently launched modeling system.
Parthoda?
Yes.
I'm here.
Yeah.
Actually, we are not able to hear you. I mean, the voice is not, it can be more, if it's possible.
Oh, okay. 1 minute.
Also requesting the admin at ICTS, if at their end, they could also increase the voice a bit.
1 minute. Let me increase my, I think, speaker. Yeah. Is it okay now?
Yeah, it's better.
Yes,
Better?
much better.
Okay, make it further.
Thank you.
Further? Better?
Yes.
Okay.
Yes.
Good. Okay. So it is still sharing, right? Still...
Yes.
Okay. So other microphone you may mute, otherwise there'll be echo.
Oh, okay.
Yeah, please. Okay, thank you. So this is a first of its kind, a very high resolution model. So I will go step by step how we have reached to this modeling system. But it is not just done by me, okay? There is a huge group of people in IITM and also some of our friends in ECMWF who very informally collaborated with us, okay? You can see them. And I will use one of my students, Kumar, was in UV, Canada. Okay, so he was also contributed. Sorry, in morning voice gets choked. Okay, so this is my outline. Okay, so I will briefly discuss about model biases in climate model, possible reason. And I'll go straight to some advantages of cube grid, which students should know. And how did we develop this model? And then performance of this model. I forgot to put, I will also add some flavor of AIML, which actually is the theme of the workshop. Okay. So this is the paper. Okay. So it is freely available. Anybody can download. Okay. And the code also is freely available. Okay. Yeah. So maybe I'll bring some water. Huh? Just excuse me. Sorry, I lost 1 minute. So this is a paper, I recommend every student published in Nature by Peter Bauer, one of the very prominent scientists from ECMWF. So why this paper is important? It is important because it gives us a very detailed account of the complexity of model when we go from, from coarser to higher resolution. At the same time, it also tells us the scales that is involved when we do modeling. Okay. As you can see here, there is a turbulence, okay, which is maybe of less than meter, millimeter scale. On. And from there, we go to subseasonal teleconnections, interannual variability, which is very large scale, which is like wave number 1, 2 kind of things. In between, we have tropical cyclones, storms, and convections, which are of, sub-daily to daily scale. So basically, all scales are interacting. And when we try to consider all of them, you see what happens is, model complexity increases when we increase the model resolution. Computing enormously increases. See, it's fully covered out system model. That is our final goal. And when we go from a very small spatiotemporal scale to a very large, hemispheric or wave number 1, 2 kind of thing, then you see coupling comes into effect. And when coupling comes into effect, then again
to interrupt, I'm very sorry to interrupt. Partho, actually, I think if you could hold your mouthpiece, the microphone, very close to, like, next to your I mean, it's I know it's a bit of an uncomfortable thing, but I think that will help us.
Is it okay now?
Yes. When you actually hold it close, it's quite.
Okay.
Yeah, sorry about that.
No problem. So you see here, so when we need coupling, people talk about coupled art system model. So we need coupling because when we go to a really low frequency mode, because ocean variations, ocean variability is slowly varying. Ocean doesn't vary very fast, right? So this, I'm not reading this, okay, but I will recommend all students to, carefully read this just 8-page paper. That is very important. It says that this thing is quite revolution. So now we are saying, I mean, the community is saying that the second quiet revolution is happening now through the hand of AIM. Okay, so we should first read what was the first quiet revolution of NWP. That is documented in this paper. Okay. Number 2, you see, this was, again, I say every meeting and every talk, a very fantastic paper. It was written by, again, our friends Wichmann, Krivdu, and Walliser, and many. Here you see, it talks about, it was actually a paper in BAMS, okay, published as a part of Year of Tropical Conversation. It is a completely virtual field campaign. We always think that, field campaign is a very expensive affair, but these guys, they tried to do a global virtual field campaign way back in, there was no COVID, okay. Yeah, so, and by the way, this YUTC data is still available at a very high distance from IFS, okay. Anyway, what you can see here is, again, the same theme what Peter actually highlighted. You see diurnal scale sitting here, seasonal scale sitting here, okay? And these are the bridging gaps: cumulus, mesoscale convective system, the synoptic sweeps, and Madden-Julian losses. So none of them are isolated. We write paper only on my Madden-Julian losses. We write paper only on synoptic, only on mesoscale, only on cumulus. But they're all connected. We cannot treat them isolated, neither in model, nor in our hypothesis, nor in our, when we analyze observations. And you see, there is also a line which is called upscale effect and a downscale effect. So if we, and I see it is written, the scale, 1 kilometer, 100 kilometer, 1,000, and 10,000. Okay. And what are the, models used? That also here. Here, I'm not going into the detail. Okay. So now, question is, I wrote that always we talk about the deadlock in convection, deadlock in precipitation. Now, what is the deadlock? So actually, we should go back to 1949. This is a paper. These are the people, very famous people. All our fathers of NWP, Von Neumann standing here, Poitov standing here, and Jules Charney standing here. So this model was recreated by Peter Lynch, and they call it CFVN, Charney, Poitov, and Von Neumann model. CFVN. And they were doing very simple job. 5th January 1949, trying to forecast the next day, 6th January 1949, 03. Okay? And you see, this is the initial analysis, this is the verification analysis, this is the starting point, this is the target. Okay. And you see, this is the forecast change. Okay. So this is the forecast, and this is a variable. So if you subtract this minus this, you get this. Okay. And you can see the circulations was here, moved here, but in forecast it is here. So you can clearly tell how the forecast is not very great because the circulation was here, it was on exactly what is line, this longitude, but here it is to the left. But question is in 1949, okay, so it was still good. And they say, Peter says that it is still useful, okay. But anyway, it was not perfect. But then when we tried something similar, it's very simple calculation. Any master degree student can do it in 1 minute. So take the NSFFNL divergence, 200 hectopascal, take the NSFFNL analysis, okay, 850 convergence. And when we are taking a look at this 26 May to 31st May, when actually monsoon onset is happening. So what do we expect? We expect a strong divergence and a strong convergence in the lower level and upper level, right? Because monsoon rain has to progress northward. That's what the analysis is showing very rightly. But then when we go just 24-hour forecast in say GFS, you see there's no sign of either the divergence neither the convergence. It is 2006, right? So we just now saw 1949. This is 2006. Okay, I will so further. This is 2010. Okay, we took WRF. We thought, okay, that's a very good model, and run it very high resolution, 15 kilometer that time. Okay, and did a 7-year simulation, 2001 to 2007, and just tried to plot considering three convection scheme available, BMJ, bed similar adjustment scheme, 10 freeze, and the Grail. Okay, we assume that Grail is an improved version of our curve. Okay, but and these are observations. Okay, and you see, we all know rain always comes in pulse, active and break, wet and dry. But what is seen here is a lull, there's a lull, and so on. But what the model is doing, it keeps raining. Okay, it keeps raining. So there is no, this intra-seasonal oscillation is missing. Okay, so we could not simulate this. Okay, now this is 2020. Okay, so the bottleneck is still continuing. You see here, this is that CMIP 3. Sorry, this is CMIP 3, CMIP 5. This is CMIP 6. Okay, this is a bias basically, rainfall bias. Okay, all ensemble model. And you see, what you see here is ocean is raining more and landing is raining less. So basically, you see a dry bias over land and wet bias over ocean. Okay, and that is irrespective of any model. You take any dam model, you see that same problem. And this is our CFS, which is used in the Monsoon mission IMD using. Okay, this is the low resolution. This is the high resolution. And this is the precipitation bias. Okay, you see the dry land and wet ocean in the high as well as low as well as high. But very perplexing is the SST bias is cold here and warm here. Okay, so irrespective of SST, it is still not deciphered why it is happening. Professor Bhatt actually asked me so many times. But anyway, I am retired. Other people will do. Here ocean is cold, and here ocean is warmer ocean. Look at this. Tropospheric temperature is cold here. Tropospheric temperature is one bias. Okay, still get the similar. So it has more element, more errors. Okay, why? Due to different mean state of temperature and ocean, you get similar rainfall bias. This can be a very good, question for any student to do a paper or project. Okay, so take this figure and go forward. Anyway, but more importantly, one of my student, Abhi, he tried to see the convectively coupled equatorial wave. I think all the students know what is convective coupling. Convective coupling in one line, if you ask me, it is nothing but rainfall, heating, and circulation. They are all coupled. You take the spectra. You take the power spectra of wind observation, 850 hectopascal wind. Okay, you take Weller, you take rainfall, you will see they are all coinciding. Okay, they are all coherent. So they are all coupled. Okay, because rainfall will release latent heat and influence the column that will influence the your wind circulation. So convectively coupled equatorial waves they play a very important role in deciding the tropical rainfall variability. Okay, It's done as an n number of paper. I'm not going into that. Now, this is observation. AVHRR at light Kelvin wave. You see how nicely it is showing Kelvin wave. Coming to CFR, there is hardly any Kelvin wave struggle. Look at this equatorial Rossby wave. That is actually overestimated. And more importantly, the mixed Rossby gravity wave, which we believe that it plays a very important role in synoptic, that was shown in Mitch Moncrief paper in YOTC and other paper. See, emergy is completely non-existent in CFS. Okay. So question is why this deadlock and what is going wrong? Very briefly, very quickly. So I think this I think students across India must have known this figure. I have shown so many times. There is Arakawa Met monograph. Please look into this. Otherwise, 1974. But in 1974 paper, this figure is not there. This figure is there in Met monograph. It is available in IITM library. You can request Sampada. She can send you a copy of something. But anyway, what does it show? It shows very simple. It shows a feedback. So large scale process. Example of large scale process. Monsoon is a large scale process. What happens? ITC moves. So control, right? What does it do? It actually modulates the moist convective instability, right? And more clear next figure. So you see here. So large scale process, ITC is your monsoon. It will destabilize the large scale atmosphere by increasing the instability and increasing the convective available potential energy. That's what moist convective energy plus adding, right? This moist convective instability, what it will do? It will generate cloud scale kinetic. That's how atmosphere comes from unstable state to stable state. That's physics. Everything cannot remain forever in unstable state. It has to come back to stable equilibrium. So it generates cloud scale kinetic energy. That's what we get in the form of weather, right? And this actually releases latent heat, warming, drying that goes and reduces the large scale instability. So this is a cycle. It's proposed by Arakawa. This is the hypothesis. What he assumed is this, that this large scale supply and the cloud scale consumption, they are in equilibrium. It's a very strong assumption. Okay, it worked very well for so long, but it doesn't work anymore. Please read this Jang paper. He has shown from observation that it fails. And we showed, okay, this is the same thing. Okay, well, Siddharth and we all in GRL 2022, we saw that it doesn't work. Any question or anything? Can we just switch off the mic, somebody's mic? Yeah, thank you. So you see here, what we showed here is the mean rainfall, okay, T126 and T382, not rainfall, I mean the decay, the difference. So you see, because the model is obeying the convective equilibrium, see the values are very less. Okay, so look at this. The color bar is not same. Okay, here blue is much higher here compared to this. Okay, so but you see, error 5 is showing no, it is not so small because models are following very obediently the Schubert. Okay, so it is giving this very low value of decay, which is actually not. Okay, that's now proved. And this is a paper by Parthasarathi with group of IIT Delhi, and they have shown, but you all know that semi-5 and semi-6 model. Basically, they use all cloud work function, the decay and similar approach, relative humidity dependence, and so on. As a result of that, we completely fail in capturing that sequence, that sequence of what Peter has showed, what Moncrief has mentioned. And here is an example of diurnal variability. You see, this is the OLR and this is the rate. Okay, what we expect. So it is early morning, midday, and this is the late afternoon. Okay, you see the OLR is decreasing. It means what? Cloud is deepening, right? When cloud deepens, the rain rate increases. That's quite natural. But what the model is doing, it keeps on running like a hockey stick throughout the day. Only thing is T2 is a high resolution model. There are many more, right? Many more data. So you get the area more prominently, nothing else. Okay, that's what she's on here. Okay, and so okay, I will skip it. Now, question is, if you take the global variance, like variability. Okay, this is synoptic variance from GPCP. This is ISO variance. It is remaining here. What is ISO? What is synoptic? Okay, so band pass filter and so on. And yeah, hello.
Huda,
Yes.
Vishal here.
Yeah.
Sorry to. So one thing that ICTS admin suggests that if you could try just with your laptop or desktop speakers, that
Okay.
without
1
the
minute.
headphones.
Okay,
So
1 minute. 1 minute. Give me 1 minute.
Sure.
Is it better now?
Can you speak maybe a couple of lines so that we could test this?
1 minute. Is it better?
I think so. I think this is better than.
Oh, excellent. Sorry.
Sorry about that. Yeah. Thanks.
Okay. So you see here, it is a GPCP, which we consider as an observations, okay, and CFS our model. What you basically see is that, the color bar is here, okay. So if you see green and blue color, it means it is a lower variance, okay. And brown and other shades are high variance, okay. You see synoptic variance is very high in northern, okay? And ISO is rather low, right? But you see over Indian region in particular and the global tropics in general, what you see is synoptic variance by the model is very low. It's the same. So it is in tune with, capturing the equatorial waves and not resolving the clouds and so on. It is continuing. It's consistent. So that's what one of my colleagues has plotted. The cloud remains same. It keeps raining. Okay? That's what one of the reasons why we get the convective rainfall too much high, okay, grid scale basically, and we get grid scale very less across the model. Okay, where in TRIM suggests it will be around 60-40. Okay, so this is I show to all my classes. So this is actually what happens in kilometer scale. Okay, you actually see the cloud is moving up, the droplets are in, the Bipin is sitting here. So you enter more into the drop, then you go into the Bipin's domain, okay, PNS and so on. But this actually is happening. We are not able to capture, so we are doing all this type of, okay. So actually, Arakor realized this, I believe. In 2013, he wrote a paper and he showed that, see, you guys, you have to get rid of mine. He did not say that. But eventually, it means that there are only two possibilities, okay, for MOXO. Okay? One is you go through multi-scale model framework. What is that? I'll come in a minute. And route one, he suggested you go straight from GCM to GCR. In 2013, we are not. Okay, but in 2025, we can. Okay, that's the point. So so that time we also tried. Okay, let us try super parameterization or MMF in CFS, and this is the basic philosophy of super parameterization. You remove closure, trigger, every damn thing. You put cloud resolving model. All this. Okay, cloud resolving model. So many, not one. Okay, it can put 10, 20, 30. The more cloud resolving model means more computing power. Okay. You can make one line, you can make two lines, and so on. So forth. You can make them talking to the nearby grid. But the most simplest, easiest, less computer expensive is this one. Okay, where I put was few around maybe 20 theorems. But they're not, you see, they're not touching the GCM grid. Okay, then how do we handle the boundary conditions? We handle it by using a cyclic periodic boundary. Okay, the U0 will be equal to U2 pi. And you can ask, is it realistic? Answer is no, it's not realistic. Okay, but still we use it. So it is a periodic boundary conditions. Okay, but this theorem will resolve the cloud. So that 1 kilometer business, this fellow will resolve. Okay, and it will give back the information to the GCM to this point. That's what is shown here over India. More engineering, I'm not going into the detail. So you can look into this. If any doubts, come back to me in email or phone or anything. So, but question is, if we do all this type of jugglery, finally we succeeded. See, in bringing the variability quite close to, if I ask you to find the odd man out, you can tell, this fellow is odd man out. But these two looks quite similar, right? So this SP has really made an impact. Okay? This is the mean annual cycle of rainfall. This is the SP stands here, TFS stands here. So drive has also improved. And this actually I did not publish, but I did this work in JPL. So I actually analyze the CRM tendencies, okay, that nobody analyzes. Okay, you will not find any paper where people have analyzed CRM. And you check EOF, the first EOF actually says, it's a shallow model. Okay, very important. So the second UF suggests the deep mode. Third UF suggests it is the stratiform. Okay, very clearly from the CRM tendency. And what we find here is the northward propagation of MJO. Okay, but what is leading is the cloud ice. Okay, so that's what gives a clear demonstration that it is able to resolve the cloud, and cloud is taking the preconditioning as well as all the heating and helping the convection to move propagate eastward. Okay, and there were paper also which suggests the super parameters help in improving the extremes. That's what US. Okay. So actually, Dave Randall and many others, they have written so many papers, and in every paper you will see this word deadlock, deadlock, deadlock. Okay. If you see this hand diagram, you actually can very clearly correlate it with those figures which plotted by Mitch Moncrief, right? You see CRMs, MMF, conventional GCM, all are connected, process level, global model. So all effort were put to connect, to make it, across the process to link my model. Okay. But then what is the issue? Then the whole world could have gone in MMF way. It did not. Why? Because of this. Too much expensive. It's running a Rolls Royce. Okay. It will go 1 kilometer, with 10-liter petrol. It cannot work. Okay. So we leave it. This is again figure from Mitch Moncrief paper. If we so then attention shifted towards global cloud resolving model. That's what route one suggested by Professor Raka. Okay, you can ask, if I ask which one is observation, which one model, is very difficult. Okay, actually this is Mitchell very close. So IFS actually showed us, we followed the footsteps of IFS. That's why two of the ESMW people were there in our paper. Okay? We greatly appreciate. Again, this is from my friend Hiroaki Miura from Jamstech. Now he's in University of Tokyo. This is a NICAM simulation. Again, you cannot figure out which one is observation, which one is model. 7 kilometers. This is observation, and this is model. So the point is, so you can actually yourself get convinced that okay, so that cloud in the box that you were showing, it seems this model is trying to simulate them. Yes, it is. And it is also simulating the ITCZ or the Pacific and Indian region quite well as compared to others. So kind of these GCRMs are, so this is basically, you can say, our motivation. And this is a very recent model by one of our co-authors. Niels Weddy was the head of modeling in ESMW. This is an operational 9 kilometer. This paper free, available in GEMS, okay, 2020. You see here, okay, see the organizations, you can see very clearly more details of the clouds when they run IFS at 1.4 kilometers. So all these gone into their into our motivations. That's how we thought that we also have to develop something of kilometer scale. Now, I don't need to emphasize here why we are doing this, why the society needs it. And very prominent authors, they have written so many papers which shows that like floods is increasing, extremes is increasing. Nothing to emphasize. Kerala is an example. It remained till today has remained as a benchmark. And the irony is that none of the model, we have to make a clear statement. And none of the model could forecast this. Okay. Here is the proof. FS is there, ESMWF is there, and NCOM is there. Okay. You can see yourself. Black is observation. Only green somehow is coming close to black. What is green? Day one forecast 24 hours. All other forecast is drastically falling. You cannot figure, this is a climatological trend. So okay, it is going almost very close to climatology. So you cannot really tell that an extreme is going to happen. So this forecast is practically of no use for warning. We published this in 2021 weather forecasting. But what is very perplexing is this rainfall was not localized. Okay, it had a large scale connection. What was the large scale connection? If you take Yana in 1973, please read this paper, okay, and take this, moisture pattern, okay. What is this is advection moisture. This is the total, the disputable water column integrated, and this is evaporation minus precipitation. You see here, okay, the column integrated precipitable water is close to zero. We were really puzzled. Now, when there is a rain that is happening, 164% or something, 30 sigma, okay, how come the precipitable water is so low? Where it is going? So what is happening is, whatever is large scale advection is happening, bringing moisture, everything is getting converted into the heavy rain, okay, and model doesn't know how to do this, okay. So you can see next figure. See, I'm not going into detail, but you can see. So none of the model is capturing this, and there was also a role played by Roxy, okay. Okay, only ensemble could capture to some extent, not much. And this is by the way, we just tried to see how the recent AIML is doing. They are neither doing very well forecast this net and GraphCast. They are also not able to see. This is observation of time. So you can't get those, hotspots. So, and this is another case, 2023, just to give you a flavor how suddenly, heavy rainfalls are happening over a city. And there is a beautiful paper by our Dr. Rajavan sir and so on. Please read this paper. This is the first paper where they have to analyze the scale. And you can see they have written very well. Frequency of short duration HREs over central India and over north is increasing. Okay, they are increasing significantly. So now this is another paper I saw in April 2025 where these people, they have used, they have compared AI and NWP model. They have used GraphCast again, but they have initialized the GraphCast by IFS and GFS. Okay, that's why they're reading Graph IFS, Graph GFS. Okay, so basically GraphCast, but initialized with IFS and GFS and compared with the actual ERA 5 and also IFS. What you see here may not be very clear, but this is 72 hour, 120 hour, and I think 190, 148 hour. Okay, so you see, what is very perplexing, not so much encouraging, is that equitable threat score is decreasing. That is natural, but for higher category of rainfall, okay, sometimes it is actually falling below the end. Okay, this is what we are not looking for. So this is very latest. Anyway, so still there is a need for kilometer scale. So now coming to the Bharat forecast system, you see the whole globe was put in octahedron, okay, like this, and there are 4 quadrants, and you put 5 points in each quadrant, make it 20 to start with. Then you put 4 more points, okay. The next, then you put 4 more points, and gradually you move towards tropics or equator. So anybody, even without going into the technical details, you can tell, so we are putting more points towards equator. That's good. Why it is good? Okay, before that, it has also some advantages. One advantage is that it is computational capacity is good, and it also cost is less. Okay, what we were bothered. So, and this is how it looks. See, Gaussian linear GFS, it looks like this, all along the, which actually from 90 south to 90 north, everywhere, it is 12 kilometer, 12 kilometer. And when you use the TCO, we come here. Okay, in Koll, it is something around or something, it comes down to around 6.5, again, just like a button. It is more closer. You can see actually near the tropics. Okay, it comes to around 6.5. And this is the grid, how it looks like. Okay, you can make out. And these are the advantages. Okay, very less time. So one advantage is high resolution tropics. You have already appreciated. Improved representation orography. This is very, 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 very important. We've drastically, have underestimated the orographic rainfall. This TCO has a very good, okay, better conservation of mass moment of energy. This is a fundamental fundamental constant and requirement for any dynamical model, which sometimes we call it negative trace. This is almost reduced. Another uh, uh, thing is diffusion. Here, normally we use filter. Okay, for this thing. Here we don't use any filter. So there is no diffusion there. And better representation of shortest high frequency wave. So all these list of advantages there, and this is just from the Niels paper, Wade's paper. You can actually see that 1.4 kilometer is capturing the deep convection better. And but before, see, we cannot jump into developing a kilometer scale model. It just doesn't work in that way. Please read this paper, 1994. Well done, Stuart. Okay, this is the first step. This is like kindergarten step. Okay, one has to use this equation. We use this equation. First, you use only dynamics prescribed by Hertz. Take these equations, run these equations, I mean the model, okay, without any physics in your coordinate. Okay, it can be icosahedral, it can be whatever, it can be TCO and so on and so forth. And you see, okay, it is given in that paper. There are some 10 figures. You just simulate those figures. If you succeed, then you can tell, okay, yeah, at least my dynamical code is set. Okay, so that's so now then you come to this complicated figure. So you build this grid first, then you run those Hertz-Suarez solve this equation in this grid, okay, and reproduce those figures which Hertz-Suarez has already done. Okay, that itself actually would took 6 months for us. Okay, if you find okay it is done, then you run with all these physics, but in aquaplanet there is no land, only ocean. Okay, and then you add land with orography, just orography. Don't add anything. Okay, and you run. So each one will take 6-7 months, no doubt about it. Then you come to vegetations. Okay, you add all these USGS and all these land use, land cover, and so on and so forth. Model will blow up. Everything will happen. Okay, you will get lots of issues. But finally, if you cross all these steps, then you reach here. Okay, you get ITCZ. That's the final step. You can check there was a film generated based on this. Okay, one very pleasing thing is that Gibbs wave, that is, they are very much in CFS, in all spectral models. You see all this type of wavy pattern, this is all spurious. And if you give it to some forecaster, he or she will feel, so these are all heavy rainfall. So no, this is all spurious, this is a noise, okay? That is almost gone. Okay? That's very good. And in a normal rainfall distributions, the tail, which is actually 1 sigma, 2 sigma, 3 sigma kind of thing, okay, maybe 2% of the total area, but the impact of those on the society is huge, right? But then you see here, this blue is TCO. It's somehow trying to, even day 5, it's trying to capture this black. Okay, so that was the kind of satisfaction for us. But heavier rainfall, I just showed you. You can check. I mean the AIML as well. And this is one example, just one example of heavy rainfall event over central India. You see TCO. This is day 5 forecast. Let's talk about day 5. Here GFS we are still to get any rainfall day 5 central India. Here we are still getting. Okay, there may be some displacement here and there, but it is holding. It is holding the moisture and producing it. That's important. Tropical cyclone is doing really good job. Okay, you can see here where the 180-hour forecast, 600 around 350 was the landfall position error. Okay, here it is just 197 200 kilometers. Okay, and this is a track error. In the shorter lead, track error is more or less similar with GFS. But in the longer lead, that's what forecaster required. Intensity as well as track, both are showing better performance. Now, giving some flavor of AIML, still there are many issues. One issue is this fellow is still taking time. Okay, now they're running it in 3 hour, 10 days forecast. But possibly you would like to have it 30 minutes, not 3 hours. 3 hour HPC time is huge. So one concept, it is a concept, okay? I think I showed in the last ICTM. This is my dream. I will be very pleased if I can do it. So Here we bring back that's SP again, okay? And we take that tendency that I showed. I use those tendencies, okay? And here, you guys, you are all of you are better than me. You build your, layers, okay? Deep layers, okay? Train them for, 90 south to 90 north, 0 to 360-degree. Get it trained, tendencies. Every grid point. That's what your GCM needs. GCM doesn't need anything. It only needs moisture source, moisture sink, and temperature source and sink. That's all. Convective parameters is giving these two only. So I get this. Once it is done, then my job is done. I don't need to depend on any closer, any trigger. Anything. Okay? That's what my friend Pierre Gentin and Stephen Rasp. You see, this is a SP cam, super parameterized. Precipitation rate and velar. And this is cloud range means that following this, you can see here, see the precipitation rate and velar. You can actually see the, southern hemispheric, it's called the waves. It's perfect. And this is damn cheap compared to this. Okay. So this will be our, so should be our next goal to go from here. I mean, use this concept, get the tendencies, train them, okay, and build your network. And okay, so in 4 minutes, I will. So this is my concluding remark. So in the backdrop of enhanced frequency of extreme precipitation events, 12 by 12 kilometers. So we had to build a kilometer scale model. There was no other alternative. Models are relatively better scale for extreme and also cyclone. Model is freely accessible. Output also, I believe, will be freely shared. Ensemble version of this model must be made in coming time. And AI/ML approach must be integrated, to represent the physics. And this model was formally launched on 26th May by Honorable Minister and it handed over to IMD. That's this figure actually. Photo is showing there. Honorable Minister, Director IITM, Secretary MOS, PGM, IMD, and Director Consumer. So yeah, I think I can stop here. Thank you.
Thank you very much, Professor Mukhopadhyay. It was really very nice talk, and you gave a very good overview of all the model, starting the history and the latest Bharat forecasting system. I hope that all the audience must have enjoyed this. So now we are open for the questions. So first, I will say that maybe online people, online audience can write the questions, and I will request Vishal to take the questions from the hall.
Right.
Sure. Bipin, I'll wait for your indication after online questions are done.
Right now there is no question, so maybe you can start taking question from the hall. If there is something in the online, I will tell you.
Sure.
Please.
So I think the floor is open for questions. I already see one hand, raised hand. So
One
please
hand, two
raise your
hand.
hand so that I know who all has questions.
Hello, sir. I am Dipan Chakraborty from IIT Kharagpur Department of Artificial Intelligence.
Wow.
So I have two questions basically. So in the very beginning of your slides, I saw there are some plot about 850 HPA zonal wind. So,
yes.
So why this is important, 850 HPA zonal wind? This is our first question. And second question is, can you please explain again what is super parameterization?
Okay. Very briefly, see, we meteorologists, atmospheric scientists, okay, we have some standard metric, okay, that we use to represent circulation. 850 hectopascal, why we choose, it is a one, actually, the height of 850 millibar is 1.5 kilometer from sea level, okay. So 1.5 kilometer, okay, is a region where we find it's not very close to surface, where we get a lot of mixtures, right? At the same time, the monsoon flow is very prominent in that 850 Along with that, 850 hectopascal or 1.5 kilometers is kind of top of the boundary line. So within boundary line, if you come within boundary line, there are a lot of things happening. Okay, Bipin will tell you what is that. lot of convections, lot of turbulence, lot of eddies, large eddies, and so on. If you take 1.5 and little above, you are free from those. Actually, you can get the background. So our aim is to take the monsoon and wind, not the local turbulence and eddy. Okay. So we take so to represent the large scale in circulation, you will see across the world people use is 850 hectopascal or 1.5 kilometer wind as a representative of lower troposphere, okay, and 200 hectopascal, which is something around maybe 10 or 11 kilometer, okay, as the upper level representative of upper. Okay, so that's how we try to explain what is happening in the lower level, what is happening in the upper level representative. Okay, hope it is clear. Now, super parameterizer. Why it is name was coined by Dave Randall and Wojtek Grabowski, both published the paper simultaneously. Okay, their intention was parameterization was conventional. Okay, so you go beyond parameterization, something supreme, superior. Okay, so they have given the name super parameterization, and you have seen the result. Why it is super? Okay, the philosophy is very simple. Okay, working is difficult. Philosophy is that you first switch off the convection, okay, which is working within the grid, okay, which is trying to get those del Q, del T, and del T, del T from the information of every grid point and trying to compute, okay, ensemble of cloud within the grid. That's what RFR was 1924. Super parameters just get rid of all this, okay, remove all this, and along one line, you put, like a pen stand, you put a single column cloud resolving model whose delta X is very high, 2 kilometer or 3 kilometer. That's what I showed the box. So there are so many 2 kilometer, like a standing cloud resolving model. Okay. But that is not in one grid point. It is there in all grid points across this thing from 90 south to 90 north and 0 to 360. So you will end up in getting, thousands of CRM. You have to do a number crunching. That's why it becomes expensive. But question is fine. But if they run, so there is a figure I did not explain. If you go, see when your delta X is 2 kilometer, due to CFL criteria, your time step also will be few steps, right? But when your GCM grid is 100 kilometer, your delta T will be minutes. So the fact is, by the time your GCM takes one time step forward, your CRM will run multiple times. Okay, all the CRM, okay, they will run multiple times. Let it run. So it is running means it is resolving the cloud, it is resolving the cloud evolution, it is doing all these things. Okay. Now, when your GCM time step again come and it is going to update everything for the next time step, it asks the CRMs, what about you? Give me my input. Then what it does, it takes average, okay, of all this. You can take a weighted mean or whatever it is, take average, and you see that grid. I showed one the slide. You see there is a black dot at every center of the grid. Through that center, it communicates those tendencies, del Q, del T, and del T, del T, okay, moisture source, moisture sink, and temperature tendency to the GCM. GCM just receives that, do all other things, okay, and then again goes to the next time step, and again these guys starts running, okay, millions of them, generates that, take average, give it to the GCM. So that's why, it becomes so expensive in running a super parameterized model. So that paper we published, we just run the model 6.5 years. We could not run it even 10 years. I hope I am able to explain to you. But you can please read all this slide I have shared with Dr. Adway. Mitra, you can take that slide. All the papers you can go through. If there is any difficulty, you can let me know.
Thank you, sir. Thank you very much.
Okay, yeah, thank you.
By the way, the slides which Professor Partho shared with me, I have already forwarded to all the participants. I hope you would have got it.
Okay. Yeah, but maybe some slides are missing. I will share these slides. Okay, that is better. If you don't mind. I added few slides today morning. I will share this.
Oh, okay, sure.
Sorry. Okay.
No problem.
Yeah, no problem.
I'm asking again in the student audience, are there any other questions? Maybe if not, I have a few questions.
Yeah,
Yes.
I allow. But students does, nowadays I don't hear any, I mean, I hear less questions from students. So that gives me either two conclusions. One is maybe all these slides are outdated. These are all very preliminary and they all know that, or nothing is understood. Two extreme. I don't know which one is correct.
Yeah, actually, we don't hear you kind of as clearly as we usually do.
Oh, is it? Why?
I kind of, what I understood was you are kind of trying to promote students to ask questions such that
Yeah. I was just asking whether students
learning would
can
have
ask more questions.
if they
But
were to
anyway,
not
no
have
problem.
vision. So I will urge students to ask questions in case things are not clear. But since we have couple of minutes, I'll just say a couple of things. One comment and one question. The comment is that I mean it's a matter of pride, I think, for all of us to see that this particular 6-kilometer model is now operational and is available as an open source code. And so on. I must congratulate you as the key person of the team and the whole team actually from IITM.
Thank you.
My question is about, so we have done some discussion about what others have done, like people like Paul O'Gorman or Bretherton, how they have tried embedding machine learning driven parameterizations.
Correct.
So regarding that, people have also reported inability to include kind of real world 3D cloud resolving model, kind of train machine learning parameterizations on 3D real world cloud resolving model.
True.
So I just wanted to kind of hear your take on that. I think that is going to be, I think, the key thing, as you probably also pointed out in second last slide or so.
Correct.
Really love to hear your kind of views on that.
Yeah. Good vision. Very good. See, I am, although I'm retired, but I am in constant touch with all these guys, Tapio and my friend Pierre, Gentil, and so on. And it is true, okay, that this concept that I am trying to tell, okay, that training from super parameterization using IML and then use it in real world 3D model. So far,
So actually,
yeah.
hear you better if you are, actually, I don't know, I have not understood why this happens, but when you are a bit farther away, actually.
Okay.
Yes.
Is it okay?
Yes, this is actually good. Yes.
Oh, very good. Okay. I thought I am coming closer to.
Sorry to bother with you.
No problem. See, the point is, no, that's okay. See, the point is, this is fact that this 3D real world application did not happen. Okay. So people are raising different problems. But see, I am very optimistic. My feeling is, see, anything you build, there will be issues, there will be challenges. Okay. But this is the ultimate. Whatever issue comes, I will request all your students, all brilliant faculties like all of you, Adway, yourself, Bipin, and everyone. You go for it. You make a consortium. Okay. Oh, you see, you tell me how this Ayuka, in Pune, consortium of astrophysics, they are now part of LIGO, and every all. Okay. This yesterday I was reading a article by Professor Ram Gopal Verma. I mean, so we cannot work in silos. Okay, even if somebody has a challenge, let us know that. Okay? Let us combinedly solve that. Okay. You alone, we can't do that. I fully agree. I am discussing with them. It is not so straightforward. Okay, it is not so straightforward. I agree. But at the same time, I also agree that it is not unfeasible. It is not that it is cannot be done. So this is the way forward. My feeling is this is the way forward. We have to, either super parameters. you use those data to train your physical parameters. The advantage is we can get rid of this unrealistic closure, which is bothering us for so many. Actually, we celebrated 50 years of our passport last year, 2024. But still, this, all symmetric model, they are still going with that same closure. This is a high time, okay? We have to make a resolution few years that no, we will train the 3D model. And we will see there are many, for example, I will tell you will not find any AI/ML model for polymer. It's not there. Okay? It's not there. If you go Google it right now, you will see it. That is needed. Okay. Radiation. I don't know. Somebody of the students, we have enough light, we have data, everything. Take that data, train this radiation. So that goes back with also. Then convection and boundary. 4 things. Okay. If you can do that and make it a part of our 3D model, I think we can resolve this deadlock. I think this title itself will never come in front of us. That's my feeling.
Yeah. Thank you, Parthasarathi. Actually, the audience was able to hear you a bit, or maybe a few words were lost. Maybe I'll try to summarize in a couple of words based on what I understood. See, he's trying to encourage us actually to go for it, just because some of the recent efforts have not been as successful. He's telling us, no, probably, but this is the way to go forward. One will have to learn things from LES CRMs, do the simulations, and try to embed them inside. And at one point, I mean, that's the words of encouragement from him. He was also saying that this word deadlock and the word closure has been around for a long time. And we have not made, people have made a lot of effort in resolving it, but it's definitely worth giving a try with machine learning. I hope, Parthasarathi, it was the...
Yes, correct. You're right.
Yeah, thank you for the words of encouragement. Is there any other question?
Yeah, Vishal, there is one question online. I don't know, Pata sir can see the from Patit Kalyan.
May I request, Bipin, can you please read the question because the audience... Yeah.
Okay, so the monsoon convection is influenced by the multi-scale process from planetary wave to major-scale systems like MCS and the Lancy Bridge interaction. How well does the BFS capture these scales, and is there any plan to couple the BFS with the land ocean models?
No. Yeah. So the point is, see, if you see paper that is published in GMD this year, this basically, gives the documents, the development part, and also the skill for like 1 year season skill and tropical cycling. Now, what actually I showed multi-scale processes, it has not been evaluated. Okay, it is generating terabyte data. I will suggest any of the students as a part of MTech project or anything, they can take up the diurnal variability, seasonal or synoptic, sub-daily scale. So it has to be done, number one. Okay. And coupling, yes. Remember that Peter Bauer's paper, okay. Land ocean coupling, yes, I think it is in the pipeline. And also soil, I think you mentioned soil, right? Soil model, right? Coupling.
Land ocean model he has asked.
Yeah. Land ocean, yeah. So land, the default GFS, whatever is using land is there, but not a complete soil model. Okay, so that also needs to be. So these two parts are not done now. It is running currently as a pure atmospheric GCM with sea surface temperature being given from near real time in our SST. Okay, and it is the SST is sustained for next 10 days. Okay, because there is no coupling. But all these things what you mentioned, certain thing can be done right now by anyone. Okay, certain thing may require a little bit more time coupling. That's my answer.
Okay, Vishal, there is no other online question. You can continue.
Sure. Is there any other question from the student audience in physical presence? Yeah, there's one question, Bipin.
Please go ahead.
Good morning, sir. Thanks for a very nice talk. I am Chitranjan. So, as you have been part of like Bharat forecast and a very good model for India. So, what did you see what challenges did you see during the development in terms of manpower as well as the computing power?
So, see, there is no manpower. You may be knowing, I don't know, if you are students or you employee or
Yes, yes. The student and like
student.
teamwork
So,
and
manpower is a big problem. I don't want to discuss it here. It's a huge problem. Okay. And more, I mean, trained manpower is another level of problem. Okay. So, we actually struggled. I honestly tell you, it took almost 5 years. You can laugh at it actually. You can tell why you took 5 years because of this manpower, because of this. We started in 2017. In between, of course, COVID was there. By 22 January, the model, that sequence was set, but it was not running. We tried in National Support Commission, ISER, that nowhere it was running. So we thought this model will not run because HPC was getting delayed procurement. Now only it happened. Government structure now. So we were kind of getting frustrated. I think we will fail. Okay? But somehow, okay, all these people who are involved.
Voice is not clear. You
Not clear?
Yeah, now it is better. Yeah.
Okay. So then, we tried again in IITM computer, okay, customization basically, okay, HPC people also helped. Then finally it started running. But for 10 days forecast, it was taking some 10-hour time, 10, 12 hours. So that is also not practical, right? But I told them, don't stop it. Let us run it. Let it take. It is like, discovering a steam engine. That will not run like Vande Bharat. It will take 3 days to reach from Bombay to Dadar or whatever. So we told, let it run. Okay, let it generate. What it is generating, we don't know whether it is generating any garbage. So we ran it like 10, 12 hours for 10 days forecast. Okay, for whatever, 3 years. Then Bipin knows very well. We got a very good, excellent computer now. Arca, right? Arca computer. In that computer, again it is customized, and now it is running in 3 hours, 10 days. So bottom line is, there is always challenge of manpower, okay, trained manpower, and there will be challenge for called HPC. We can't help it, but for that we can't stop our research, right?
Okay.
Our innovations, so we have to keep on continuing.
Good. So actually, Chitranjan worked on the NICAM model at IIT Kanpur. So maybe Chitranjan, you can also contribute in this development of BFS.
Yeah. Everybody should. That's what is the purpose of making it free. I mean, open source.
Or maybe the machine learning part he can
Yes.
contribute.
Everybody.
Bipin, there is one more question that Chittaranjan wants to ask. Do we have time for that?
We only 10:33. Maybe he can write directly to Mukhopadhyay sir. He is giving the email now, and
Yeah.
he will start the next talk.
Agrees to that. Yes.
A Google form has been shared with all participants. So if anyone has any further questions, please fill it up and I will collect them and forward them to the speakers.
No. It will be fine. Perfect.
Yeah, thank you, Parthoda, on behalf of all the audience, kind of physically present here. Over to Bipin.
Yeah, okay. So we again thank Professor Partha. And so this session is now over. And
Thank you.